So first of all, it's a great pleasure and honor to be here. It's nice to see all these known faces. It's like going back 10, 15 years in the past. So what I'm going to talk a little bit is the work that I've been doing in the past 2 years. Actually, I started this work here while I was doing my sabbatical. And it's related to state estimation in distribution grids. So smart grids, everybody is aware, is one probably of the grand challenges of this century. And in fact, this is the problem of innovating the largest machine ever built by mankind. So it's a formidable endeavor. So a power grid has already witnessed the penetration of renewables. And in general, we divide the power grid into two parts. We call it transmission grid, the part with high voltage that is responsible to deliver energy from large power plants to basically urban areas. And then we also define distribution grid as a medium to low voltage network that actually delivers that energy to the final user. So renewables has already a reality in transmission networks. So we have a big windmill plants and photovoltaics. What is a little bit slow and less penetrated is smart grids into the distribution network, where you want to have solar panels at each household, smart buildings that can turn on and off appliances or dim down lights, and electric vehicles. So a traditional distribution grid has a tree-like structure where basically there is a transformer that transforms medium voltage energy into low voltage, and then power flow is basically one direction, and that goes from the transformer to the household and the small business. So we are only dealing with typically with passive loads. The grid is oversized for peak loads, and so far there has been no need for real-time monitoring. But things are going to change when we are going to introduce distributed renewable resources, because this basically will a possibly reverse power flow. So flow we will go both directions. That might create problems in safety breakers, because they are being designed for having monodirectional flow, and also there will be very rapid power flow changes depending on the weather. So there is a clear need for real-time control and management at the distribution level. So why smart grids are not yet a reality at the distribution level? So the good news is that we have the technology to do that. So microgeneration technology is there, and is relatively inexpensive. We also can embed smartness, that is like a computation that can take autonomous decision. Also remote communication via wireless or power over line communication. There is also a wide public acceptance for renewables, and also enterprise and investors are ready to find a new revolution in order to where to put their money on. But what is preventing this to be a reality? So there are a number of reasons. I listed here only some. There are some macroeconomic context problems that I will describe in a second. Also, it basically requires a real-time load and demand balancing with very intermittent and stochastic sources. Also, there is a problem in terms of trust of distribution operators on these new technologies. And finally, there's also a little bit of problem in terms of energy, that storing that at the distribution level is still a little bit too expensive, but is also very important in order to optimize the performance. So I want to spend 1 minute on these two problems. So the first problem is everybody is aware of this macroeconomic slowdown in the past 5 years at worldwide level. And also more important is this battle on price for oil. This is just the graph for the past 2 years. And now oil costs very little, so there is little incentive from that point of view to turn into renewable resources. But this is just a temporary problem. The other major problem is that operators are very reluctant to use smartness in their grid, because basically this means that they have to delegate the power, and they don't know what's going to happen. And this is a safety critical infrastructure. So what they really want to know is that your system that you are going to implement will do no harm. So you want to avoid catastrophic failures, like cascade failures, under typical condition that when you have communication in place, you cannot avoid random delay, packet losses, and also you have some uncertainty on the model. So you want to make sure that you're not doing worse than before. The second thing is that they want the system to be alive. So they don't care too much at some point of performance. They just want to know that you can guarantee continuous operation even under some infrequent but critical events like communication blackouts, local failures, new agent installation, and cyber attacks. And finally, if these two imperatives are satisfied, then you want to make it better. So you want to improve performance. And I think that as a community, we have focused probably a little bit too much on the third point, which is not the key ingredient to make the operators to accept the new technology. So let me give you a little bit of a control perspective for smart grids. So we have the physical system, we have the typical sensors, actuators, blocks, and here the controller. So what we do in control is that we take a sensor measurement and we try to decide which are the right control input in order to make the physical plant to behave as we want. Another thing that we do is that quite typically is that we try actually to do the control by first using an estimator that estimates the state. So you have a better view of what's happening in the grid, and that additional information will help you providing better control. I want to stress a couple of things that besides an estimate, you can also build uncertainty. So you can also estimate what is the uncertainty on your estimate. And this is very important in this type of systems where you have communication in place or other events like failures and cyber attacks and new system installation. So uncertainty is not constant over time, but changes. So you want to design a system that when your uncertainty is small, then you can go and use feed-forward controls, like to be very aggressive and to go really after performance. But when you have high uncertainty, then you need to be very careful, and you have to back up and use feedback to be more conservative and look at stability rather than performance. So what does it mean, state estimation in the context of a smart grid? So basically, in a distribution grid, you have a point which is called point of common coupling that is responsible to keep a certain voltage profile, which is an alternating current. So there is a nominal value. And then you have this tree-like grid where at each node you have, again, a sinusoidal wave that represents the voltage, but with a different magnitude and phase. So under ideal condition, basically, each voltage at steady state is represented by a sinusoid. And therefore, we want to represent that with a phasor. So that means that it's a vector, it's a complex number with a certain magnitude and phase. So there are two ways to represent them, either via polar coordinates, magnitude and phase, or Cartesian coordinates, like real and imaginary part. So why voltage phasors are important? They are important because basically they provide a global picture of what's going on in the grid. The reason is that if you also have the additional information about impedances of all the different lines, you can readily compute line currents. And then if you have the line currents, you can also compute the current going through the different loads. And once you have currents and voltages, you can compute the power flow on each line. And also you can compute the exact power flow on each load. So basically, if you can compute the phasors at each node, then you are done. So which are the sensors in this type of systems? So the sensor, there are two types. One is called a phase measurement unit. So basically, it's a device that is placed at some node that is provided with GPS, timestamp, and some signal processing device that is able to estimate the voltage or the current phasor. So basically, you can measure both magnitude and phase. And the typical total vector error, so the magnitude of the difference of these two complex numbers, goes from around 1% to 0.1. The other type of information we have comes from smart meters. So they can measure active and reactive power, possibly average over 5 to 15 minutes. And therefore, basically, for each household, potentially, you have a time series that can help you to predict the profile of the user for example, the next day. As for the actuators, instead, what you have different types of devices. Some are controllable, some are not. Typically, for example, could be a battery or a solar panel with an inverter, a passive load like a load bus, or an active generator like a PV bus. So typically, you are not able to control the voltage or the current, but you control the power flow that you can inject or extract. So basically, typically you control the active power or the reactive power or both or some combination. There are some cases where you can control directly the current and the voltage, but it's much more complicated and expensive. So summarizing, basically, a grid state estimation gives you a global picture of the grid. And this is not an application per se, but it's an enabling technology, because then you can use for voltage regulation, stability monitoring, contingency analysis, dispatching for detection, topology identification, and not last, control. However, this is a hard problem that has been well studied in transmission grids since the 70s by Schwepp and Wiles. It is a hard problem because it's a nonlinear stochastic problem. Also, an additional problem that we have in distribution system is that the lines are more resistive, while in transmission they are more inductive, and therefore we cannot use a typical approximation model like the DC model, for those who are familiar with this type of models. And also, another important thing is that we cannot map a three-phase system into a single-phase system as we do for transmission, because in distribution, typically the three-phase are not balanced. So we have to deal with the three-phase simultaneously. So let me give you a little bit of intuition behind the problems that we want to solve. So basically, you have a grid. At each grid, you have associated a voltage and a current that is either injected or extracted, depending if you have active or passive load. And this is the relation that you have. So L is called the admittance matrix. For those familiar to distributed system, this is very close to a Laplacian, and is a sparse matrix. And that basically tells you once you know the voltages, you can compute the currents, and vice versa. Also, we have this additional constraint, which is the point of common coupling works as an ideal voltage generator. And here where the problem comes. So basically, this is the nonlinear term. We know that the power flow at each bus is the product of the voltage times the complex conjugate of the current. And typically, that's what you know. So what is given is the value for S, not for V and I. V and I are your unknowns. And you want to solve the set of equations. So this is actually called the power flow problem. So basically, you are given the values for the loads, the value for the nominal voltage, and the Laplacian, that is the topology and impedances at each line, and you want to solve it. So basically, at the end of the day, you get this n-dimensional complex number that represent the phasors of the system. So in a transmission grid, these are how typically look like the different phasors. So basically, they are spread all around. They are tried to be kept within a certain ring through voltage support, but the phase you see is spread all around. Fortunately, in distribution grid, the situation is different. So the phasors actually don't move too much. And the reason is that there is no much power flow and the lines are much shorter. So you see that with respect to the nominal value V0, the voltages are quite close, within 10% typically of this center. So the idea here is very simple, is why not replacing the true voltage phasor with a nominal value? It seems quite a simple idea, but has a very important consequences. So basically, remember, this is my system that I had before. These two pieces are linear. The nonlinear one is this. So what I will do is that I will replace the true voltage phasor here with the nominal one. Of course, this is an approximation, and that will generate an error. But now, if I do so, I can compute explicitly the current, which is a linear relation with the flow, and I plug it back into here, and then I get a linear expression between the power flow and the loads, the active and reactive power at the loads, and the voltage. So this is basically now my system, which is linear. If now I add some information that I can extract from the smart meters, I have I have some knowledge about these loads, some nominal values and some uncertainty that I can extract from the time series. Also, I have some PMUs, so some devices that can measure directly the voltage that are affected with some noise. And everything is linear, so if I want to find which is the optimal estimate of the voltage, basically it turns out to be a Bayesian linear unbiased estimator. So it's a very simple solution for this problem. And here we tested this idea on a 123 node test feeder. And here you see basically the estimation error as a function of the number of PMUs that you add. And we compare basically the traditional approach that is based on the true nonlinear model, the one that we expect for our linear model, and here are from Monte Carlo. And you see that the match is quite remarkable. So even if we made a mistake in linearizing the system, the uncertainty that we have here is much larger than this. So we can safely neglect the nonlinearity here, at least in distribution networks. So summarizing, what we have seen is that you actually need a much finer resolution for voltage PMU in distribution network, like 0.1 as compared to 1% in transmission. But you can get by with a larger estimation error if you can measure currents. But this is in general more expensive. Also, it's important to add dynamical modeling for the loads in order to apply Kalman filter and improve the performance. And again, I told you that it's very important that we address the three-phase problem from the very beginning. And also we need to include the topology impedance uncertainty, but since the mode is linear, I think there is a good hope that we can manage that. Also, other important problems regards optimal PMU placement, because those are expensive, so I want to use as few as possible. And finally, in order to get very good performance, I need to have a very fine time synchronization in PMUs. Okay, thank you very much.